right, guys. Is there anyone here who hasn't collected the test paper, the in-class test paper? I got a big pile of papers that haven't been collected. You guys collected all your papers, guys? Seems. All right. So, do you guys have questions? I'm sure you have plenty of questions. Maybe you're too afraid to ask or something. Just feel free to ask, guys. Any past paper questions, in-class test questions? Come on, guys. Just give me a shout, please. Just ask me a question, guys. I've got copies of the past exam papers, so you can tell me the number. I will look it up. You should tell me the year and the number. I will do it happily. You have only 2 weeks left for the exam. And come on, guys, please. And you started revising yet, or is it? Or you do it the day before or something? You do the revision day before the exam? Yeah? Come on, guys, please. Any questions, guys, please? Any questions you have? No? Sorry? 91. Okay. Which one is that? What? This one? I thought it's one of 91. This is one of the questions in the problem sheet. I think I did it in the last week tutorial. I did this question in the example class last week. So I suggest you look at the podcast for example class last week. I did this question, sir. Any other questions, guys? 90? Yeah, I did this too last week. Come on, you guys, some of you guys don't come to the example classes, so I suggest you look in the podcast. If you look at the podcast for the example classes last week, I did both these questions last week in the example classes. All right, let's start with something. All right, let me do example. Oh, come on. Example 82, right? Which is this one here. So you're testing, sorry. All right, so you have So this is example 82 from the examples booklet, this one. And this is basically the summary of the example. You have a sample from a normal distribution with these parameters. Sigma squared is known. And we are testing this versus this. And you are told the type 1 error probability is equal to little a, and the type 2 error probability is equal to capital B. And the question is to show that sample size n is equal to this. Okay? Now, the first thing you must work out is the rejection rule. In this case, you will reject the null hypothesis if what? You have ideas? Come on, guys. What is the rule for rejecting H0 in this case? This is where you need to look up in the notes, guys. You see here that, do you remember this, guys? We have mu equal to mu 0 versus mu not equal to mu 0. That's one possible scenario. The second case is where mu equal to mu 0 versus mu is greater than mu 0. That's the second scenario. The third is where mu is equal to mu 0 versus mu less than mu 0. Now, of the three scenarios, which of these will belong to? This one belong to? Come on, it's an easy question, guys. Yet, I'm sure there are three possible tests you can have. You can have mu equal to 0, mu equal to mu 0 versus mu not equal to, mu equal to mu 0 versus mu greater than, mu equal to mu 0 versus mu less than. Right, which of the three will this belong to? Less than, of course. Yeah, so the rejection rule is if it's this one here. So alpha in this case is A, remember. Because remember, alpha is the probability of type 1 error, which in this case is denoted by A, right? So this is the rule for rejecting the null hypothesis. The question is to find the value for n. So I'm going to use this fact here, that is B is the probability of remember, type 2 error, we did this quite a while ago, right? I know it's been a while, but type 2 error is the probability of accepting the null hypothesis when H1 is true. This is H1, this is accepting. So this is the probability that accepting is the complement of rejecting. So this would be root n All right. Now, how do we simplify this, guys? Remember, we are conditional. The conditional statement says that we are conditioning on the true mu, the true population mean, equal to mu1. So what should we do now? We should change this guy here, this is no longer the true population mean. The true population mean is mu1, not mu0. So the next thing we must do is to change. I mean, I've done this several times. You should know. You should be bored by this now, guys. Do you know why I'm doing this, guys? The reason I'm doing this is because I want this to be the true population mean, which is mu1, not mu0, right? Now I'm going to put brackets around like this. Now I'm going to take this term here to the right-hand side. So this will become yeah. All right, now let me ask you something. What distribution does this have and why? I mean, I asked this question 100 times already. Not 100 times, maybe not like 10 times, maybe more than 10 times. You should know. I mean, what distribution this has? Standard normal, right? Why is that? Because the conditional on mu equal to mu1, that the true population mean is equal to mu1, this must have the standard normal distribution. Do you know why, guys? Some of you seem lost. I don't know why. Look, remember, this is a property that I talked about in week 1 of this course, that if you have a random sample from a normal distribution, then the sample mean also has the normal distribution with these parameters. And it's because of this that this must have the standard normal distribution, right? Okay, so this is Is that clear, guys, or not? Are you okay with this? Yeah. Yeah. All right. Now this you can write as 1 minus the probability that yeah, and this is 1 minus phi or phi okay. Yeah. Are you with me so far? Any questions? All right. Now this guy here, it must be equal to capital B. Now the question is what is the value for n? N is the sample size. So what we need to do now is to solve this equation here for n, right? So that's what I'm going to do now. Put this over here. Put this over here. I'm going to solve this equation here for n. So that becomes this is just standard stuff, guys. So the root of n is equal to sigma and finally, taking the square both sides, you get n equal to, check whether I'm getting the right answer, yes. So n is equal to sigma squared times right, and that's the answer that we are supposed to show, right? So the sample size n is equal to this, right? Is that clear, guys, or not? So this is example. This is what I did is if you just came in, this is example 82 in the examples booklet. Yeah, this one. Example 82. All right, guys. Any questions? Is that clear or not? It seems a lot of people have gone home. I see not many people here. You guys finished the other courses or no? Not yet. No? You have? Okay. All right, other questions, please. Yeah, any other questions from the examples booklet or any from over here or from over here? Any questions you want me to do, guys, please let me know. Huh? – 2006. Let me see. Takes me a while. Is it this one? Or you mean this one? This one? Yeah, the last one is basically asking you whether the power function in part C is most powerful in the sense of NP llama. So to answer this question, all you have to do is whether you just need to check. Remember what I told you about the NP llama. Any rejection rule that is obtained using the NP llama is the most powerful test. So to answer this question, you just need to go back to part B, right? This is part B, yeah? And check if the rejection rule that you got over here can be obtained using the NP llama. Oh, does it make sense? Or maybe I would do it, okay. I think maybe, all right. Maybe it doesn't make sense what I say, don't know. So this is exam 2015, 16, question 5, part D. Okay. All right. Now to do this question. Well, it's asking you whether the power function in part C is most powerful in the sense of the Neyman-Pearson llama, right? So basically what you need to do is you go back to part B and ask the question whether the rejection rule for this one and this one can be obtained using the NP llama, right? So let's consider let's consider 2, right? I know, I mean, one can be done. There are 2 cases. You need to consider this one and then this one, but I would do just the second one. Let you do the first one. All right, here you have mu. Okay, so you have mu equal to mu0 versus mu less than mu0. Now, in order to apply the Neyman-Pearson lemma, I'm going to rewrite it like this. I'm going to rewrite this as mu equal to mu1 less than mu0, right? Because otherwise, you cannot apply the NP lemma without a simple hypothesis. So I'm writing this as a simple hypothesis. So instead of saying that mu is less than mu0, I'm saying that mu is equal to mu1, but mu1 is a number that is less than mu0, right? You see what I'm saying? Because like in this current form, you cannot apply the Neyman-Pearson lemma, right? So then you can say that by you can say that by the Neyman-Pearson lemma, we reject the null hypothesis if the ratio of the likelihoods is less than a constant C, right? Now this will be so this is the likelihood at mu0, and this is the likelihood at mu1, right? A few things cancel. This guy cancels out with this guy, right? So what you have what you have is this, right? This simplifies to this, yeah? And, okay, further simplification. Yeah? Yes? Now simplify this, you get if you open the brackets, right, and simplify things, I'm not going to show you every step. I'm sure you've done this hundreds of times. I'm sure you probably know better than I do. So you will get something like this: 2 mu1 sum of xi plus n mu1 squared plus 2 mu 0 sum of xi minus n mu 0 squared less than a constant. You get something like this. You should do the simplification correctly, right? And this can be further simplified as just bear with me, guys. Okay, like this, okay? And let me put this over here. Carrying on. Now the next thing I'm going to do, I'm going to take the log both sides. So I'm going to take the log on the left and the right. So it will become this. Yeah, you should take the log on the both left-hand side and right-hand side. You should get this. And then what's going on? Just give me a sec, guys. Yeah. And finally, I'm going to divide both sides by mu0 minus mu1. Now, before you decide to divide both sides, you must determine the sign of mu0 minus mu1. Now, if you go back to the beginning of this question, of this problem, you will see that mu1 is less than mu0, right? So that means mu0 minus mu1 is a positive quantity, right? So you should divide, you get this, right? And you can call this, because this is, for the sake of notation, you can call this a constant K, right? So the rejection rule by the NP lemma or the Neyman-Pearson lemma, the rejection rule for the hypothesis that, for this hypothesis, is that X bar, the sample mean, is less than a constant K, right? Now, to answer the question, the question over here is whether the power function in part C is most powerful in the sense of NP llama? To answer that question, you need to go back to the lecture notes. You will see that for this hypothesis, that is, for the hypothesis that mu equal to mu 0 versus mu less than mu 0, the rejection rule in the lecture notes is this one, right? Equation 98. Now what you have here is of the same kind as this. I mean, the only difference here is that here you have x bar subtracted something and multiplied by something less than or equal to minus z alpha, which is of the same type, as what I have here. Because obviously you can write 98, equation 98 in the lecture notes, right? Can be written like, just bear with me. It can be written like this, right? This is what you have, right? Now, if you rearrange this equation, what you have is x bar less than plus mu 0 minus z alpha sigma divided by root of n. And you can call this, it the same constant k, right? So the rejection rule that you have here is of the same type as the rejection rule that we got by the NP llama. And therefore, the answer to the question is that this rejection rule was obtained by the, so what this means is that 98 is a most powerful test, right? In other words, the rejection rule was obtained by means of the NP llama, and therefore it must be a most powerful test. Or in other words, the power function based on this must be most powerful in the sense of NP llama, right? Is that clear or not? Does it make sense? No? Is it too much words? No. I mean, you just need to check that in order to answer questions like this, what you need to do is you just need to, oh, where am I? You just need to, not this one, where's the sheet gone? It's here, yeah, here, oh no, not this one. Yeah, you just need to, what you need to do is you need to write down the hypothesis and apply the NP llama, like I've done here, and derive the rejection rule, which turns out to be this one, x bar less than a constant k. And see if this rejection rule matches up with the rejection rules in the lecture notes, which it does in this case, right? Because according to the lecture notes, equation 98, the rejection rule in equation 98 is of the same form as x bar less than a constant k, right? Therefore, the test given by equation 98 is the most powerful test. Yeah. No? Are you guys okay or not? Some of you seem lost. Was it too late in the day or what? Huh? Sorry, guys. Anyway, any other questions, guys, please? We still have half an hour left, guys. Please ask me more questions. Maybe it's something less difficult, I don't know. Huh? Guys, please. I mean, you only have like 2 weeks, less than 2 weeks for the final exam. I believe that mine is the first exam, right? Is it not? Not for you? Some people have mine as the first exam. I don't know whether it's good news or bad news. I don't know. They have mine as the first exam. Any other examples from the examples booklet, like this one? Any other examples you like me to do, guys? I think I did. Any other examples, please, guys? Part B of question 6. Oh, just a moment. Where is mine? Is it the one involving maximum? Is that right? I thought I did this before. Anyway, I'll do it again, guys, if you want me to. It's this one here. So this is exam. (2015-16), question 6B. So you have right. So once again, you start off by saying by NP lemma, we reject H0 if the likelihood at theta 1 divided by likelihood at theta 2 is less than a constant, say k, right? Oh, is it? Can you see it? Okay. Right, now we have a sample of the density function. Sorry, guys. The density function is this one here, the exponential of theta minus x. Yeah? So when you write down the likelihood function, it's this one, and you should put the indicator function also, that xi is greater than theta. You follow what I've done, right? The density is E of theta minus xi multiplied by the indicator function that says that every xi must be greater than theta. Oh, sorry, theta 1. Is it theta 1 here? Sorry, guys. Theta 1. Okay. And similarly, in the denominator, you must have theta 2 minus xi Yes? You with me so far? And simplify this, guys, you get take the product of this, you get E of n theta 1 minus the sum of xi, I from 1 to n. Now the product of the indicator functions you must know, because that's one of the formulas in the formula sheet, right? Yeah, is that not? You remember the formula sheet for the exam, which is on my website for the course. So what's the product of these guys? It's the product of the min of xi is greater than theta 1. I'm sure you looked at the formula sheet, right? Yeah. So you should the product of that is the min, right? And in the denominator you have theta 2 minus okay. Now if I have a red pen here, these two cancel. Yeah. Okay, so you have what you have is E of n theta 1 minus theta 2 times okay. Now, if you look at the left-hand side, yeah, the only term that depends on the data is the min of xi. This min of xi is the min of xi. So, basically, what you have here is a function what you have in the left-hand side is a function of the minimum of xi. And I call that function g. You can call it any other name, but just I call it g, okay? Now what I'm going to do next is I'm going to draw a graph. I'm going to draw a graph of the function g versus min of xi. So let's see how it's going to look like. So suppose this is min of xi, and suppose this is g min of xi. So I'm gonna graph this function here as a function of the minimum of xi. Now we know that theta 1 and theta 2, theta 1 is less than theta 2. Suppose theta 1 is here, and suppose theta 2 is here. Now to determine the graph, I'm going to take three points. 1 point over here, 1 point over here, and a point over here. And determine in each of these three segments what the value of this function is. Now let's consider this one. Now if you are here, what is the value of this, guys? If you, for this point, what would be the value of this? 0. And this? 0. So 0 divided by 0 is undefined. So basically, the function the function is undefined on this side, right? Okay. Now let's take this point here, that is between theta 1 and theta 2. Right? This one is equal to 1, and this one, this one is 0, and this one is, oh, am I right? Sorry, no, I'm confused. This one is 1, yeah, this one is 0, right? So 1 divided by 0 is infinity, right? Okay. So between theta 1 and theta 2, you have between theta 1 and theta 2, the value of this function is plus infinity. Suppose this is, I know plus infinity does not exist, but let's suppose, for the sake of argument, let's suppose it does, right? So between these 2 points, the function takes this value, right, which is plus infinity, right? Now, let's consider this point here. Now, over here, this will be equal to 1, and this is also equal to 1, okay? So 1 divided by 1 is 1. So you have a constant outside. So the value here will be equal to E of n theta 1 minus theta 2. Right? I don't know whether you can see this. So the value over here is E of n brackets theta 1 minus theta 2, close bracket. So the function g is a step function, plus infinity over here and a finite value over here. So it's a stepwise decreasing function. Can you see that? Right? Because it is plus infinity between these 2 points, and thereafter it takes a finite value. Right? Therefore, when you take what I'm going to do is I'm going to take the inverse functions both sides. So I'm going to multiply by the inverse of I'm going to multiply it by the inverse function of g on both sides. But g is a decreasing function, right? Now, when you take the inverse of a decreasing function, right, you need to change the signs around. Do you know that? That if g is an increasing function, then you don't need to. But here you are taking the inverse. You're from this line to this line, you are taking the inverse of a monotonic decreasing function. So the less than sign here must become greater than, right? So in other words, the min of xi, this is equal to min of xi, must be strictly greater than a number like this, which I call C. Is that clear, guys, or no? So that's the answer to the question, guys. Does that answer you or no? No? Some of you seem lost. Does it make sense or not, guys? No? Okay. Because when you take, if a function is decreasing, I thought you might know this from analysis or algebra or something. If a function is decreasing and you take the inverse and you have an inequality involving that function and you take the inverse both sides, then you need to change the inequality sign. So if the inequality was less than, taking the inverse both sides, it will become greater than. Yeah, like here, you have less than here, guys, right? But you should take the inverse. You should take the inverse, G inverse here. Then it should become greater than. If you don't know it, just write it down, guys. Okay. So that, but you don't. That's only if it is decreasing function. If it is not. If it is an increasing function, you should not change the sign of the inequality, right? All right, other questions, guys, please. You got my email yesterday, right, about the office hours for the final exam? So I'll be in my office until the 23rd of May, which is a Tuesday. So feel free to come and see me. Yeah, of course, we have a class tomorrow too, yeah. We have a class tomorrow, so you can ask me more questions tomorrow. And we have an example class today from 5 to 6. You can come to that too. But after this week, I'm talking about after this week, I'll be in my office and at the stated hours in my email to you. So feel free to drop in and see me anytime in the times I gave you, right? And of course, you can also email me 24 hours, 7 days a week. Yeah. Okay. All right, guys. I hope. By the way, had you collected your test papers? Because I still have a big pile. I carry this back around all across the university, hoping somebody will collect their papers. But it seems nobody wants to. Hi. Hi. Hello, sir. You got your paper? What's your surname, sir? G? M, is it? Yeah. So how did you find the test? You did very well, right?
I got 15.
Yeah, that's very good, man. Okay. Yeah, yeah.
Your previous lecture,
Okay.
previous notes. Here, this example. Usually we stop here.
Yes. Is it M? What's this?
G.
G. Okay. Just a minute. Let me check this up. Just give me a sec, madam. Can I put it over here? You guys check. It's under the A to Z order.
No, I don't specify.
Okay, thank you.
Here.
Thank you.
Are you waiting there?
Sorry.
Here, I think
Sorry.
this example.
Yeah, yeah.
Usually we stop here after we find MA. And why do you continue doing this?
Yeah, that's because you're told that lambda must be strictly greater than 1.
Yeah.
Yeah? All right? And so that's why you need to continue doing this, because there's a restriction on the possible values for lambda. So if this number is greater than 1, then the MLA is 1 over x bar. But if it is less than 1, then you need to plot the likelihood function.
Oh, okay.
And you will see that in this case, in the second case, the MLA is equal to 1.
Yeah, okay.
Okay?
Thank you.
Try to see if you can follow. If you can't follow that, just come back and see me.
Okay.
Yeah.
Bonus question.
Bonus, yeah. Is it bonus? Yeah.
Yes.
Okay, good. It should be under G, sir.
Yeah.
It should be under G.
Yeah.
Or whatever your surname is. You found it?
Yeah.
Oh, good, good.